So our next example kind of shows us the deBroglie wavelength in action. And so in part A, it says to calculate the deBroglie wavelength of a baseball traveling at 99 miles per hour. And so I think we did this in our thermo chapter too, and there shouldn't be a question mark here, but that's okay. And so we have the mass of a baseball at 0.145 kilograms. And so what I've done here is I've taken this 99 miles per hour, like I think we did previously, and I've converted it to meters per second. And so we just take our 99 and we do our 1609 divided by our 3600. Yeah, I think maybe in a previous chapter it was 95. I was just confirming that we had the right number. We do 44 meters per second. And now I'm just going to plug all this in to the deBroglie wavelength equation. And so again, h is 6.626 times 10 to the minus 34th. Now what I'm going to do is I'm going to break up my joules here into kilograms, meters squared per second squared, and then times seconds. So this is my joule seconds. And so what I've got here in parentheses, that's my joules. The joule is a kilogram meter squared per second squared. And then I'm going to divide that by my 0.145 kilograms, and I'm going to divide by my 44 meters per second. So don't forget that when you divide, that flips everything upside down, so the seconds end up back in the numerator again. And so if you look at how the units all work out in this, I'm going to get rid of all my clutter here. There we go. If I look at how all of my units work out here, what we basically find is that my kilograms drop out, my second squareds drop out, and one of my meters drops out, and that leaves me with just meters, which is kind of cool. And so the wavelength of a baseball thrown at 99 miles per hour off a pitcher's mound is 1 times 10 to the minus 34th meters. Now remember that our metric prefixes only go up to like 10 to the ones we've learned about anyway, only go up to like 10 to the minus 12th or 10 to the minus 15th. So this would be a really small number even if we were measuring this in nanometers or picometers or something crazy. This is basically, for all intents and purposes, approximately zero. So at the macroscopic level, when someone throws a baseball, do I need to be concerned about wave-particle duality? No. I can think of the baseball as a particle. All of the classical physics equations that just deal with particles and ignore all the wave stuff, it's perfectly fine. But let's repeat the same calculation for an electron. And we're traveling at 6 times 10 to the 6th meters per second, so about 1% of the speed of light. It seems fast, but compared to the speed of light, this isn't really that fast. The mass of an electron is 9.1 times 10 to the minus 31 kilograms. And I will also tell you to note that the approximate diameter of an atom is only about 10 to the minus 10th meters. So if I calculate the wavelength of this electron, I do all the same things. My kilograms all drop out, one of my meters, and all of my seconds drop out. I end up with 1.2 times 10 to the minus 10th meters. This is approximately the same size as my atom. So what I'm basically saying is if my atom is this big, the electron's wavelength is about that big. And so that's definitely significant. That's something I can't ignore. And so at the atomic level, the deBroglie wavelength is important. The next example deals with the Heisenberg uncertainty principle. It says, what is the uncertainty of position of a baseball in the previous problem if its speed is measured at 1.99 or at 99 miles per hour plus or minus 1%? So we're going to take Heisenberg's uncertainty principle here and we're going to divide both sides of it by m delta u. So we can get the uncertainty in position by itself. Notice that this is an inequality, not an equation. So it says that the uncertainty of position will be at least this much, greater than or equal to. It could be more than what we're calculating here, but it will be at least this much. This represents a minimum value. It can't be smaller than this. So again, we're going to plug in Planck's constant. This actually ends up very similar. The only difference is instead of using speed, we're using the uncertainty in speed, and there's also this factor of 4 pi in here. But from a unit standpoint, it works out exactly the same as the deBroglie wavelength formula does. And so when we plug in h, we plug in our 4 pi, we plug in the mass of our baseball, and then because our 99 miles per hour, remember this was 44 meters per second, I took 1% of that. So I multiplied it by 0.01, and I get 0.44 meters per second. This means that the uncertainty of position of a baseball is 8.3 times 10 to the minus 34th meters. Again, compared to anything that we could possibly see or pay attention to with the naked eye, this is basically zero. So yes, the little tracker on Fox when you're watching baseball and it shows you where the pitch was, that's probably pretty accurate. We can absolutely pinpoint where particles are when we can actually see them with our eyes. But again, if we do this in part B for the uncertainty of position of an electron, when again that speed is 6 times 10 to the 6th plus or minus 1%, and we have our mass of our electron given, again note the approximate size of an atom is 10 to the minus 10th. Plug in all these numbers again, we get that the uncertainty of position is going to be greater than 9 times the size of the atom. So basically what this means is that if my atom is here, what I can tell you with some certainty is that the electron is somewhere in here. Some volume that's approximately 10 times the size of the atom itself. And so good luck trying to pinpoint electrons is basically what Heisenberg's uncertainty principle tells us. Again, at the level that we can see, Heisenberg's uncertainty principle has no bearing on our everyday life, but when we start to study atoms down at the atomic level, this becomes very important. So the takeaway here, again, if you don't want to get into all the math, that's fine, but the takeaway here is that electrons move as waves, and that their wavelengths are significant, and that we have really no idea at any given instant in time where an electron is. They're moving around very quickly, and they're skipping between these energies, these quantized energies. And so where we'll go from here is we'll try to make sense of all this and sort of put all this together in a modern quantum theory.